Okay, I'm going to jump in and catch up with you. And I'm going to sit in Jeremy's desk today. Oh, good. If I get thirsty, I got some Gatorade or something. Oh, it's just water. Okay, yeah, that's what they all say. Vodka, probably, right? Gin, some other clear alcoholic beverage. I know you, Jeremy. This is recording, by the way. Write a general equation of a function f of x of lowest degree, which has the roots of 3 plus 5i and 3 minus 5i. Put it in reduced factored form. Okay, first of all, what do we call 3 minus 5i and 3 plus 5i in relation to each other? Conjugates. Yeah, they're conjugates of each other. So I can use the factor theorem. F of x equals, I can put an a in front if I want. It's the general form. I'm not sure what a is going to be. We don't have information, but we can write the a in front if you want. But really, it's going to be x minus one of the roots. That's the factor theorem. And x minus the other root. Yes, yes? If a is a root, then x minus that number is a factor. So I'm going to put 3 plus 5a here, and its conjugate 3 minus 5i here. Now, just like we did in the previous section when we had radical binomial roots, we're going to go off to the side here on our workbench, and we're going to expand that out. So the first thing I'm going to do is distribute the negative. So I get x minus 3 minus 5i, and then x minus 3 plus 5i. Okay, I saw y'all doing that, so that's good. And now FOIL doesn't work, so we'll just distribute. I'll start with the x and distribute all the way through. So we get x squared minus 3x plus 5ix. I'll switch flavors now. I'll distribute the negative 3 minus 3x plus 9 minus 15i. Switch flavors one last time. Distribute the negative 5i, and you get negative 5ix plus 15i. And then here we get minus 25i squared. So that's the careful expansion. It's not difficult. It's a little bit tedious. Now, if we do this correctly, everything that has an I, just like everything that had a radical, should cancel. So we got a positive 5ix and a negative 5ix, a negative 15i and a positive 15i. Make sure that they do, in fact, cancel. So now I can just write my result. I get x squared. I have a minus 3x and a minus 3x. That's a minus 6x. And I got a plus 9 right here. And look at this on the end. I have a minus 25i squared. What's another name for I squared? Negative 1. That's right. So a negative 25 times a negative 1 really makes that a what? A positive 25. That's right. So anytime you see like negative 25i squared, you can just call it positive 25. So really my numbers then are 9 plus 25. What's 9 plus 25? 34. And there is the answer in expanded reduced factored form. All I got to do is bring it back in over here to the project, and I get a times x squared minus 6x plus 34. And if we had an ordered pair that we were trying to force this to go through, then we can go ahead and find the value of a. But right now, we'll just leave it in general form. And that's it. Okay? 3 plus 5i, 3 minus 5i. Questions on that? All right, let's go back to the notes. Give us the notes. We love our notes. We got to example 4 yesterday, and we did pretty much the exact same thing, didn't we? 2 plus 3i was the root, and 2 minus 3i was the root. And just like on the warm-up, we had a conjugate pair of imaginary or complex roots. That leads us to this theorem today to summarize it. Here's what the complex conjugate theorem says. It's real easy. It basically says if a plus bi is a root, then a minus bi is also a root. You can't have one without the other. It's like a horse and carriage, like love and marriage, all that good stuff. It's very similar to the radical conjugate root theorem that we had that said if a plus the square root of b is a root, so is a minus the square root of b. Okay, so I don't have to give you both of them. All I have to give you is one, and you tell me what the other one is. For example, if I tell you that I have a root of x equals 2 minus 5i, what do you know is also a root? 2 plus 5i is also a root. That's right. Here's another example. What if I tell you negative 3i plus 4 is a root? What's the other root? Ah, you didn't take the bait. It's positive 3i plus 4. Very good. It matters which one you change the sign on, doesn't it? You have to change the sign of the I one. If this were a multiple choice question, guess what answer choice A would be as the conjugate? Negative 3 minus negative 3i minus 4. That's wrong, isn't it? Okay. If you want, you can first write negative 3i plus 4 in a plus bi format. That would be 4 minus 3i. Now you could say if 4 minus 3i is the root, so is 4 plus 3i. So it's very important that you know that you're changing the sign of the I part, not just the middle term. Got it? Okay, so now we've avoided a potential trap on the test, right? By the way, speaking of the test, we are going to test on Friday, but a lot of people are testing on Friday because it's the end of the 3 weeks when everyone needs to test. And Friday is an odd day, and math is technically supposed to test on an even day. So we're going to move the test on to Monday. So we're testing on Monday, which I think is the 6th of November, which is an even day. And it'll be 3.1 through 3.4 minus 3.3. That works out well for you. I know it's a Monday test, but you got the whole weekend to prepare, and it gives us an extra class day to review. Okay, that's what it does. So I was going to try and circle back and do 3.3, but Coach Richter just said, no, let's just take an extra day to review. And I was like, okay. So that's how it works, guys, when you talk to women you respect. Okay, just say, yep, that's right. Yeah. Oh, the quiz will be tomorrow. Oh, what is the quiz over tomorrow? It's over section 3.4. From example 1 to example however far we get today. You'll have 2 questions. Yeah. You'll have one question like the warm-up or like example 4. You'll have one question like example 4, and then you'll have one question like example 5 through whatever, 5 through 8. Okay, that's how far we're getting today. So you'll have one question where you're creating the equation, and you're going to have to go off to the side and expand just like we did in the warm-up. And then you're going to have another type of question where you're going to be doing synthetic division and solving and finding the roots. Okay? Great question. Any other questions? All right. Let's jump into example 5 then. It says, using your factoring abilities only, find the complete factorization and all the zeros for the polynomial. Okay. So what is the degree of this polynomial? 5. It's degree 5. So the fundamental theorem of algebra says that I'm going to have exactly how many complex roots? 5, right? They may be real, they may be imaginary, they may be double roots or triple roots, but when I add them all up, including the multiplicities, I get exactly 5. That's how I know the search is over. All right, now, they didn't give me any roots to begin with, so I have really nothing to start with synthetically. But I do have my factoring ability. So if I set this equal to 0, which is our first step in solving, we set the equation equal to 0. Once it's equal to 0, we try to factor by using the zero product property. And the first rule of factoring is what? Look for a common factor, a GCF. Do we have a number that's common in all 3? Yes, 3. Do we have an x that's common in all 3? X, right? So if I factor it out, I'm left with x to the 4th plus 8x to the 2nd plus 16. And it's still equal to 0. All right, now I can focus on this right here. This right here is actually factorable, okay? As long as you have something that's x to the 2n plus, let's call this a, bx to the n plus c, this could factor as long as this is twice as big. Now, we're used to doing it with just x squared and x to the first, right? We're used to just seeing it with x squared and x to the first. But it works the same way when you have x to the 4th and x squared. Let's see if we could double bubble this puppy, okay? What would the square root of x to the 4th be? It would be x squared, right? So instead of putting an x in the first slot now, I put an x squared. And you can check, when you FOIL it out, what would x squared times x squared give you? X to the 4th. Now, when you multiply the product of the inner and outer, they're going to be x squared terms. So it's really the same idea. What are the factors of 16 that add up to 8? 4 and 4. And they both have to be positive, don't they? So really, this turns into 3x times x squared plus 4, quantity squared. Quantity squared. All right, now I can set each of the factors equal to 0. So either 3x equals 0 or x squared plus 4 squared equals, squared equals 0. Well, if I solve this, I get x equals 0. That's no big deal. What's the multiplicity of that root? Yeah, his exponent is 1, so that's a multiplicity 1. So that's one of the 5. Now notice that how many roots are left in this other factor group. I have an x squared, but they're both double roots, right? So the x squared plus 4 is going to give me 2 roots, and both of those roots are going to be double roots. So does that give me the 4 that I need? Yes, all right. So let's go ahead and take the square root of both sides. I get x squared plus 4 equals plus or minus the square root of 0, which is 0. And then I'm going to separate. I get x squared equals negative 4. I take the square root of both sides, and I get plus or minus the square root of negative 4. Now off to the side here, what's another name for the square root of negative 4? Well, that's the same as the square root of 4 times I. You can do that every time. We're doing that right now in Algebra 2, so I know you've seen it before. If you ever see a negative under a square root, just bring it out to the side and call it I, because remember, I is the square root of negative 1, as Jeremy presciently saw yesterday. All right, now, is 4 a perfect square? Yeah, so really we can go one step further here and say the square root of 4i is really just 2i. So this becomes x equals plus or minus 2i. And because that was originally a squared factor, what's the multiplicity of each of those roots? Those are both multiplicity 2. So how many roots did we find just right there? Plus or minus 2i multiplicity 2 is actually 4 roots, right? 2i and negative 2i, and then another 2i and another negative 2i. They're imaginary bounces. So there's 4 roots there, plus the one over here that we found is 0. We found all 5 roots, didn't we? Yeah. Now, how many real x-intercepts are we going to see? We just see 1. This graph is guaranteed to have at least one x-intercept that's real because it's an odd degree, and it only has 1 real x-intercept. So it's going to wiggle a bunch off the x-axis. So let's go ahead and list the roots. So, in our final statement, so f of x has roots of x equals 0, comma, plus or minus 2i. Let's actually list them with multiplicities. I like that better. 0, m1, and plus or minus 2i, m2. That way anybody who knows what they're doing knows that we've accounted for all of them. Okay. No synthetic division needed there. We just factored. All right, comments or questions on that one? All right, what might that one look like? I'm glad you're asking. Well, it might come in like this. It comes in the bottom. It's going to cross through 0, and then it might look something like this. Instead of just going up, it's going to have some extra wiggling going on. This wiggling off the x-axis, these are the imaginary roots. Okay, that's kind of what it looks like. That's how it manifests on the real number line. It wiggles off the x-axis. But we only have one nice crossing real x-intercept, plus some wiggling going on. All right, let's look at example 6. Using the rational root theorem and your graphing calculator, find the simplified exact value of all the roots. That is going to become kind of a trite little instruction right there. Find the simplified exact value of all the roots. That's kind of what it's going to be the rest of the period. All right, the rational root theorem, remember, tells us this. If I'm expecting rational roots, that is integers or fractions, those are the relatively nice roots, they're going to be of the form p over q, where p is a factor of the constant and q is a factor of the leading coefficient. So my constant is negative 4. That's going to be my p. And then my constant is 3. That's going to be my q. That was not a very good 4. Negative 4. There we go. So let's list the factors of the constant first in the top. That's plus or minus 1 and plus or minus 4. And then it's plus or minus 2. The factors of the leading coefficient are q. That's plus or minus 1, plus or minus 3. So the possibilities now in the form p over q are going to be as follows. Plus or minus 1 over 1, plus or minus 4 over 1, plus or minus 2 over 1. So it's just those 6 right there. And then I put the top 3 over 3, and I get plus or minus 1/3, plus or minus 4/3, and plus or minus 2/3. None of those simplify down to one we've already gotten. So how many distinct possible rational roots are there? This could be a multiple choice question. It could say how many distinct possible rational roots are there? We have 1, 2, 3, 4, 5, 6 positive and 6 negative for a total of 12. There's 12 distinct possible rational roots. Are any of those guaranteed to work? Nope, not a single one of them is guaranteed to work. We could have entirely irrational roots or imaginary roots. But if we were interested if any of those work, we would only have 12 to try out. And if we went through the whole list of 12 and none of them worked, then we would know the remaining roots are either irrational or imaginary. There's no guarantee of a real root, is there? Because it's an even degree. Now, we're going to use the calculator to help tip us off. Instead of just doing random trial and error, we're going to use the calculator to tip us off. So let's go to the calculator, go to the Minnesota link, or you could jump up and grab a yellow one if you really want to. But the Minnesota link in your Canvas is very, very helpful. Now, here's what I have found. If you size the window before you load the calculator, it's easier. So once you get to this, instead of clicking the calculator button, go ahead and bring your Notability window back in, size it down to 1/3, and now click the triple bar, click the calculator, and then remember you hit the double A button and you hide the toolbar, and now the calculator shows up beautifully. So get the 1/3 of the window first. I always got the calculator first and then the 1/3 of the window, and I was shuffling the calculator around. But get the 3rd window, then the calculator, and then hide the toolbar by clicking on the double A. And now it's set there ready to go. So now we'll hit y equals, and we'll type in our equation. We hit 3x caret to the 4, then you click to the right, minus 2x caret to the 3rd, and you click to the right, and then it's minus x squared, so you can hit the squared button, so you don't have to click to the right anymore, minus 12x minus 4. You double check, make sure that it's the right equation, because you could have fat fingered something or been careless. And then we hit zoom 6. Zoom 6 is your standard -10 to 10 window. Zoom 6. And it looks like that. It doesn't quite look like a parabola because it doesn't have the symmetry. So it looks like it's going to be higher than a degree 2, which we know it's a degree 4. But let's zoom in and see what we can find our roots to be. Let's look at the positive root first. I think that's the easier of the two. It looks like it crosses where? At x equals 2. Is 2 in our candidate list? Yes. Now here's how you can verify on the calculator. Watch. From the graphing screen, just hit the trace button, and it's actually waiting for you to type something in. So type 2 and hit enter, and it blinks right there and says it's 0. So yes, I'm going to go ahead and write that down. We know x equals 0 is one of the roots. I'll put roots colon. Okay. And then the next one, is it -1/2? Is -1/2 in our candidate list? It is? No, it's not. -1/2 is not in our candidate list, so it can't be -1/2. But it could be what? -1/3. Let's see if it is -1/3. Hit the trace button again and type in -1 divided by 3 and hit enter. And what does it tell us? It is a 0, right? So -1/3 is also a root. Oh, I put 0 instead of 2. Thank you. Yeah, we confirmed 2. I wrote down 0. I don't know why I did that. Thank you. So it's 2. We confirmed 2, and now we confirm -1/3. Now, is that all we really need to find the rest of them? If it's a 4th degree polynomial, and I have 2 roots, I can synthetically divide it down to get 2 and x squared. And of course, once we get to x squared, we've got it made, don't we? Because we can either factor it, or at the very least, we can use the quadratic formula. Are you ready? I'm ready for it. All right, little Taylor Swift there. Let's write down our coefficients in descending order. We're going to do some synthetic division here. 4, 3, 2, 1, 0. So it is written in standard form. So here we go with the coefficients. 3, -2, -1, -12, -4. And I draw my line now. I'll synthetically divide with one of them, and I know I'm going to get a 0. Does it matter which one I start with, 2 or -1/3? Which one makes more sense to start with? 2. It's easier on yourself if you start with the easier one, because then when it comes time for the -1/3, you'll have one fewer columns to work with. All right, because every time we synthetically divide, we get rid of a column. All right, bring down the 3, multiply, you get 6, add, you get 4, multiply, you get 8, subtract, you get 7. That gives you 14, that gives you 2, that gives you 4, and we got a 0, just like we knew. So those are the coefficients now of the remaining cubic. Those are the cubic coefficients. But we don't need those because we've got another root. So we'll just draw another panel here. And now we'll do negative 1/3. We'll bring down the 3. We multiply, we get negative 1. We add, we get 3. We multiply, we get negative 1. We add, we get 6. 6 times negative 1/3 is negative 2. And lo and behold, we do in fact get a 0 there, just like we wanted. And now we're staring at the coefficients of the quadratic, right? It started at degree 4, then 3. Now we're at degree 2. So now we'll just rewrite these. We'll say, so 3x squared plus 3x plus 6 must equal 0. And now it's like we have a brand new problem. We found 2 of the roots, but now we're still stuck at the quadratic. What's the first thing that we're going to try to do when we set it equal to 0? Factor it. We prefer to factor it if it works. And what's the first rule of factoring? GCF. Do we have a GCF? Yes, 3. So I'm going to factor out the 3, and I get x squared plus x plus 2. And now I can focus exclusively on the nice-looking quadratic inside the parentheses. Does it factor? Are there factors of 2 that add up to 1? Only if we subtract them, yes? Well, because the product is positive 2, they have to both be positive or both be negative. So 2 plus 1 is 3, and negative 2 minus 1 is negative 3. Is there any way to get 1, though, if we can't subtract? No, so guess what? It doesn't factor. Pooper scooper. Guess what that means? We get to use the quadratic formula, which I know everybody in here still knows. It's on the back board if you would like to refresh your memory. Okay, it's in blue. We're doing it right now in Algebra 2. You should memorize this because I'm not going to give you this on a quiz or a test. But if ax squared plus bx plus c equals 0, then x is the opposite of b, plus or minus b squared minus 4ac under the radical all over 2a. You got it? You remember that? You shouldn't have got out of Algebra 1 without memorizing that. So our a is 1, our b is 1, and our c is 2. So here's the solutions using the quadratic formula. It's the opposite of b, so it's the opposite of 1, plus or minus the square root of b squared, which is 1 squared or 1, minus 4 times a times c, all over 2a. All right, now I need a new column, so I'm going to come over here, and I'm going to simplify that. That gives me negative 1 plus or minus 1 minus 8. That's the square root of negative 7. All over 2 times, oops, I put a. A is really 1. I should put 2 times 1 there. All over 2. Now, notice I have the square root of negative 7. Come off to the side. If you ever see the square root of a negative number, what you should do is call it the square root of a positive number and put the I on the outside. Because the square root of negative 1 is I. So the square root of negative 7 is really the square root of 7 times I. And make sure the I is on the outside of the radical. Now, is 7 a perfect square? No. Does it simplify at all? Does it have any perfect square factors? No, it's prime. So I could just bring that back in over here and get negative 1 plus or minus the square root of 7 times I on the outside all over 2. Now, the last thing we do is we split it up. We want to put it into a plus bi format. So we're going to get negative 1/2 plus or minus the square root of 7 over 2 times I. And there are your 2 complex conjugate roots. Negative 1/2 plus the square root of 7/2 I, and negative 1/2 minus the square root of 7/2 I. You can't have one without the other. The quadratic formula has it built in. Now notice that if it was a positive square root of 7 under the radical, then the radical conjugate theorem would have been at play, right? Then I would have had 2 radical conjugate solutions instead of 2 complex conjugate solutions. So let's list the roots. So the roots of f of x are colon x equals negative 1/2 plus or minus the square root of 7 over 2 times I, comma, what are the other 2 roots that we already found that were real? 2 and negative 1/3. So how many did we find total? We found the 2 complex conjugates, that's 2, plus the 2 and the negative 1. We found 4 roots. What was the degree of the polynomial? 4. Is the search over? Yes. Okay, the search is over. Now this one's going to see 2. It's going to come in the top and go out the top. It's going to cross the x-axis twice, but then it's going to wiggle off the x-axis. Okay, and that wiggling is what's going to cause it to, it's going to look something like this if you want to graph it. Here's negative 1/3. Here's 2. It's going to come to the top. It's going to cross. It's going to cross. And then off the x-axis, it's going to wiggle or something like that. And this wiggling right here is what the imaginary roots are going to be responsible for. So it doesn't look like a parabola with 2 single roots. It has 2 single roots like a parabola, and then it wiggles off the x-axis like a parabola would not. All right, comments or questions on that? Y'all could do synthetic division, right? So you'll have one question like the warm-up and like example 4 on the quiz tomorrow, and then you'll have one question like example 6 where you're given some information and you're going to have to synthetically divide. But the fun is just getting started when it comes to synthetic division today, boys and girls. For I have in store for you more math candy on this Halloween. Example 7. Find the simplified exact values of all the complex zeros. Okay, that's going to be the instructions for the rest of the day until we get to the last question. 4. Negative 13 f of x blah, 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 if 3 minus 2i is the root. Okay, step 1, take stock. What is the degree of f of x? Is it written in standard form? Yes, no. Or no, yes. Is it ness or is it yo? It's not, is it? So our first step should be to write it in descending order of degree. So x to the 4th minus 10x cubed plus 36x squared minus 46x minus 13. It was written in ascending order instead of descending order. All right, now we know it's a 4th degree polynomial. How many complex roots is it going to have with multiplicities? It's going to have 4. If I can find 2, I can get it down to a quadratic by synthetic division, and then I can find the rest of them either by factoring or the quadratic formula. I need to know 2. Diggity darn it, they only gived me 1. 3 minus 2i. Or did they implicitly give me 2? For if 3 minus 2i is a root, what must also be a root? 3 plus 2i. How many do I now have? I have 2. Is that enough to divide down to a quadratic? Yes. Okay, now, we have not synthetically divided yet with imaginary roots. This is going to be your first go at it. So, step 1, write down the coefficients in descending order, leaving a placeholder for anything that's missing, and put a little bit more space in between your numbers. Ajani, are you with us? Ajani, are you with us? Hang in there. Let's write down, we're on example 7, Ajani. Let's write down the coefficients. Leave a little bit more space in between there than usual. 1x to the 4th, negative 10, 36, negative 46, negative 13. A little more space than usual. You'll see why here in a second. And then out front, we put our box, and we know we're going to get a 0 in the remainder box at the end. Now, which one should we synthetically divide with first? The 3 plus or the 3 minus? If we want to help ourselves and keep things nice and tidy. I would do the positive first, yeah. So let's do 3 plus 2i. All right, so now we start the process. We bring down the 1, we multiply by 1, and we get 3 plus 2i. Now, just like we did when we did this with radical binomials the other day, we have to add like terms in this column, which are the numbers. What's negative 10 plus 3? Negative 7. So I get negative 7, and then I just bring the plus 2i down. Now's where it gets fun, okay? Because now I have 3 plus 2i times negative 7 plus 2i. Guess where I'm going to do that multiplication? Off to the side on my workbench. Yeah. 3 plus 2i times negative 7 plus 2i. Don't be afraid to go off to the side and do this. Foiling is what we have to do. We have to FOIL off to the side. So if I FOIL, I get negative 21 plus 6i minus 14i plus 4i squared. And now I simplify. What's another name for positive 4i squared? Negative 4. So if I add my numbers, I get negative 4 minus 21. That gives me what? Negative 25. And then I add my I terms together, and I get minus 8i. That's what we want to bring back into the synthetic division in the next column. Negative 25 minus 8i. So you see why we wanted a little bit more space in between our numbers than usual, because we actually have a binomial all the way through here. Now I can add vertically, and I add like terms. So 36 minus 25 gives me 11, and then I bring down the minus 8i. Guess what I get to do again off to the side? More foiling. So 3 plus 2i, this time times 11 minus 8i. And here we go. Distributing the 3, we get 33 minus 24i. Distributing the 2i, we get plus 22i minus 16i squared. And this is probably where you start thinking to yourself, I'm doing this wrong. The numbers are weird. I'm doing it wrong. But no, have faith. Keep going. Let's do the i's first since they're right there. Negative 24 plus 22, that's negative 2i. And then tell yourself, hey, self, what's another name for negative 16i squared? Positive 16. And then I can combine that number with this number to get what? 49. So I get 49 minus 2i. Now you really think you're doing it wrong, right? Well, let's just keep going. Bring that in. We get 49 minus 2i. And things all of a sudden start looking hopeful for you. What's 49 minus 46? I get 3 minus 2i. Holy moly smokers. I got to do this one more time. 3 plus 2i times 3 minus 2i. How are those related? They're conjugates of each other. And if you remember from Algebra 2, when you multiply two complex conjugates together, you get a number. Let's see what number that is. Distributing the 3, we get 9 minus 6i plus 6i minus 4i squared. Your 6i's, in this case, cancel. And the minus 4i squared is another name for what number? Positive 4. And then I combine the positive 4 with the positive 9 to get what? Positive 13. I put that over here, and it worked out. It worked out. Don't just put a 13 there because that's what you're expecting it to be. Actually do the math and make sure you get to 13. That way you know the other parts are right. Okay, now, what should I synthetically divide next? If I knew another root, should I use it or should I do the conjugate next? The conjugate. So I mentioned this when we had radical conjugates. Always divide your conjugate roots back to back. It just makes it easier. So even if I knew another root here, I would still do the conjugate root back to back. Otherwise, you're going to make it very, very difficult. The numbers get ugly. Okay? But if you do the conjugate root back to back, numbers will get pretty again all of a sudden. Watch this. Bring down the 1, multiply, you get 3 minus 2i. Hey, what happens with your 2i's? They cancel and we're left with negative 4. Sweet. Now we distribute. I think we can distribute in our head, can't we? I get negative 12 plus 8i. My 8i's cancel and I'm left with negative 1. And then I distribute the negative 1 and I get negative 3 plus 2i. And I add and I get what? 0. Well, looky there. We did it. We got it down to a quadratic. So that's what this means right here. So we have x squared minus 4x minus 1, and that has to equal 0. And let's see if we factor that. Are there factors of negative 1 that add up to negative 4? No. Shucks diddly darn it. We get to use the good old what again? Quadratic formula. Yes, yes. So A is 1, B is negative 4, and C is negative 1. So that means x must equal, and this is where the Algebra 2 kids messed up on their quiz yesterday. If B is negative 4 and the theorem has a negative B in front, that's the opposite of B. What's the opposite of negative 4? Positive 4. Plus or minus the square root of B squared. Be careful. What is negative 4 squared? 16, not negative 16. Be careful when you B squared. So B squared minus 4 times A, which is 1, times C, which is negative 1. All of that over 2A, which is 2 times 1. All right, now I just simplify that. I get x equals 4 plus or minus. What am I going to end up under my radicals? 16 plus 4? That's positive 20 all over 2. Now, I don't get imaginary solutions here. I'm going to get 2 real radical solutions. So off to the side now on my workbench. I'm going to focus on 20. Is 20 a perfect square? No. So remember, in order to simplify the radical, you either know what the largest perfect square factor is, or you get this prime factorization. It's 4 times 5, which is 2 times 2. So the prime factorization is 2 times 2 times 5. Remember, because it's the square root, it takes a pair of 2's on the inside to become 1 on the outside. So the square root of 20 actually equals 2 times the square root of 5. Because it was originally 4 times 5, and the square root of 4 is 2. So if you just knew that the square root of 20 was 2 times square root of 5 without having to do the prime factorization, that's great. Now I'm going to bring that back in over here, and I get x equals 4 plus or minus 2 square root of 5 all over 2, and I'm almost there. The last thing I need to do is split it up. Give each term in the top of the denominator. So 4 over 2 plus or minus 2 square root of 5 over 2, and now I simplify. What's 4 halves? 2 plus or minus these 2 divide out, and I get the square root of 5. Hey, I get a pair of conjugate irrational solutions. That's the radical conjugate theorem from last section. If 2 plus the square root of 5 is the root, then so is 2 minus the square root of 5. The radicals become plus or minus. So the roots of f, we can list them all now. The roots of f of x are x equals 2 plus or minus the square root of 5, and what are the other ones? 3 plus or minus 2i. If they're all M1s, you don't need to say that they're all multiplicity ones, but they all are M1s. We found 4 distinct roots. 2 of them are real, 2 of them are imaginary, and it's a 4th degree polynomial, so they all have to be multiplicity ones. You don't have to write that. All right, y'all can do that on a quiz, right? That's like a good second quiz question right there. I like that one. Very quiz-worthy. Quiz-worthy. All right, comments on that, questions on that, how we proceeded. It should be getting kind of fun, shouldn't it? You should be getting good at it. It's a little bit tedious. You have to be meticulous, but it's not that difficult. If you're okay with foiling off to the side on your workbench and bringing it back into the project, you should be fine. It's the people who are reluctant to do that. They're like, I'm going to do it in my head. Garbage, garbage, spill, spew, garbage, stink, stench, septic tank. And it goes sour. It goes to pot. But inch by inch, it's a cinch. Mile by mile, it's a trial. All right, let's try example 8. I think you can like example 8. Do we have time? Yeah, we have time. Find the simplified exact complex roots of f of x, which is a 5th degree polynomial, given that negative 3i is a double root of f. That means it counts twice. It works twice in the synthetic division. Well, that gives us 2 roots then, doesn't it? Negative 3i and negative 3i. Is that enough to get x to the 5th down to a quadratic? No. If I divide out 2 x roots from x to the 5th, that leaves me with x to the 3rd. I would need at least 1 more. Hey, isn't negative 3i an imaginary root? So doesn't the complex conjugate theorem tell us that if 0 minus 3i is the root, that 0 plus 3i should also be a root? Yes. And if it's a double root, shouldn't positive 3i also be a double root? Yes. So how many roots do we actually have? We have 4. We have x equals negative 3i, multiplicity 2, and then we have positive 3i, multiplicity 2, by the complex conjugate theorem. So we have 4 roots. I can synthetically divide out 4 things and get it down to a linear instead of a quadratic. Those are even easier to solve. Let's go ahead and do that. Write out the coefficients. 1x to the 5th, negative 2, 18, negative 36, 81, 162. All right. Now, which one do you want to divide with first? 3i or negative 3i? Let's do positive 3i. Okay, here we go. Bring down the 1. Multiply, you get 3i. Add, you get 3i minus 2. Now, you could go off to the side and do this, but I think we could do this in our head because it's just times 3i. It's not a binomial. What's 3i times 3i? It's 9i squared. But wait, don't write down 9i squared. What's another name for 9i squared? Negative 9. Very good. And then distributing, we get 3i times negative 2. That's minus 6i. Are you with me? And now we add vertically. 18 minus 9, that's 9. So we get 9 minus 6i. Let's distribute again. 3i times 9, that's 27i. And then I'm going to get 3 times negative 6, that's negative 18i squared. What's another name for negative 18i squared? Positive 18. There you go. And now I add like terms vertically. I get 27i minus 18. Now I multiply by distributing again. 27 times 3, that's 81. I times I is I squared. Yeah, so I get 81i squared, which is negative 81. And then 18 times 3, negative 18 times 3 is negative 54i. And then the 81's canceled just to leave me negative 54i. And if I multiply, I get negative 162i squared. And what's another name for negative 162i squared? Oh, I'm sorry. I'm off by a negative now. What did I do wrong? I'm supposed to get a negative 162. Oh, that's where I went wrong. Yeah, they weren't going to cancel. Thank you. That should be a negative 162. I wrote it down wrong. Yeah, my synthetic division was going swimmingly. This becomes positive 162 and I get 0. Whew! We dodged something there. Okay, last question. We won't be able to finish this today, but I know 3i works again. Should I do 3i again next? No. What should I do next? Negative 3i. Very good. Because remember, we said you should always do what? Your conjugate roots back to back. Now, let's just finish this off and see what happens. Bring down the 1, we get negative 3i. Multiply, you get negative 3i. Add, you get negative 2. Your i's should cancel as you go through this next iteration. Oops, I brought down, sorry. Why did I do that? I brought down a 1 and then negative 3i. There we go. And now we get negative 2. You multiply and you get 6i. Add, you get 9. Multiply, you get negative 27i. Add, you get negative 18. Multiply and you get 54i, and you get 0. And that's as far as we'll get today. So that brings us to a third-degree polynomial. And we have 2 more roots. Tomorrow we're going to start by doing 3i again, and then negative 3i again, and that should lead us to a linear coefficient, which we can solve, okay? All right, but that's all tomorrow after the quiz. And we're testing when? Monday. All right. Thanks for your cooperation today.